Okay, so welcome again to the One World Mathematical Game Theory seminar. Today we are hosting Mira, who, as far as I can see, has almost a complete sweep of the most prestigious universities around the world. On the west coast of the US, she's been associated with Stanford and Berkeley. On the east coast of the US, she's been associated with Harvard, Yale, and Princeton. She's now at Yale. And in Europe, she's been at the École Normale Supérieure in France and in the University of Oxford in England. So I don't know if I need to add any more. Go ahead, Mira.
Okay, thank you very much for the introduction and for the opportunity to present as part of the seminar. So I'm going to present joint work with Lyota Ijima and Yuta Ishii, and Lyota is actually also on Zoom. So if you want to ask him questions in the chat, feel free to reach out to him. Okay, so coordination problems under uncertainty about a payoff relevant state of the world are ubiquitous in economics, from joint investment and technology adoption decisions to currency attacks, bank runs, and many other settings. Now, as is well known in such settings, there are two important obstacles to coordinating on an efficient outcome. First, players' first order uncertainty about the state, and second, their higher order uncertainty about other players' beliefs. And so given this, a natural question is to understand which information structures are more effective at reducing both these types of uncertainty and hence at facilitating coordination. And so in this paper, we address this question by conducting a comparison of multi-agent information structures in a learning setting. Specifically, we assume that players have access to many draws of private signals from an information structure, where you can think of the idea that they see many draws of signals as capturing that data is cheap or abundant. And we assume that these signals are generated independently across draws, but may display potentially arbitrary correlation across different players' signals. Our starting point is a seminal result due to Cripps, Mailath, and Samuelson, which shows that in this setting, under some natural assumptions, we get common learning, meaning that all information structures are going to induce approximate common knowledge of the state in the limit as the number of signal draws goes to infinity. However, importantly, this result is silent about which information structures accomplish this more effectively, so are more effective at reducing both first order and higher order uncertainty. And so to understand this question, in this paper, we take the natural approach of comparing which information structures lead to faster common learning, in the sense of inducing a greater chance of approximate common knowledge away from the limit, so after a large but finite number of signal observations. So specifically, our first main result in the paper precisely characterizes the speed of common learning under each information structure. And our characterization is based on the key insight that I'll be highlighting throughout the talk, that we show that under every information structure, higher order uncertainty, in fact, vanishes faster than first order uncertainty. And as a result, we show that the speed of common learning simply coincides with the speed at which individual players learn the state. And we characterize this by means of a simple learning efficiency index. And second, we apply this characterization to obtain a ranking over information structures in terms of their value in coordination problems. In particular, we show that information structures with higher learning efficiency lead to better equilibrium outcomes in all coordination games that are played after sufficiently many signal draws. And as I'll discuss, this yields some robust implications for information design in games played in data-rich settings. So just briefly to put this in context, so our paper contributes to the very rich literature on higher order beliefs. Now, a central insight in this literature is that higher order uncertainty can be an important source of inefficiency in coordination games, reflecting the fact that even when first order uncertainty is small, higher order uncertainty can still be significant. In contrast, in this paper, we highlight that in natural learning settings where players have access to many signal draws, higher uncertainty vanishes faster than first order uncertainty and eventually becomes negligible relative to first order uncertainty. To make this point, as mentioned, we focus on the common learning framework of Cripps, Mailath, and Samuelson. But our key contribution relative to theirs is to conduct a comparison of different information structures in terms of the speed at which they approximate common knowledge. And then our analysis of the speed of common learning builds on Moscarini and Smith's characterization of the speed of individual learning in single agent settings, as I'll discuss in a moment. And finally, this paper more broadly relates to the large literatures on information design in games and comparison of information structures in games. Let me skip the details. One key difference is that we focus in this paper on data-rich settings where players have access to many signal draws from each information structure. Okay, so here's the learning environment. There's a finite set N of agents, a finite set theta of states, and agents share a full support common prior P0 over states. An information structure I consists of a space Xi of private signals for each agent I, which we assume is finite. Let X denote the set of profiles of private signals, along with a joint distribution over profiles of signals in each state. And I'm going to denote this by mu theta. So this joint signal distribution allows for arbitrary correlation across player signals. And we let mu I theta denote the marginal distribution over player I's private signals. We assume that all these marginal distributions, mu I theta, have full support, and that they're distinct across different states, theta and theta prime. And so we're going to be interested in settings where agents observe not one, but repeated IID signal draws from an information structure, where T is going to capture the number of signal draws. Okay, so let me first start by reviewing the important result due to Cripps, Mailath, and Samuelson that this setting gives rise to common learning. And so formally, for any p between 0 and 1, let BTP of theta denote the event that all agents individually p-believe state theta after T signal draws. So all agents individually assign probability at least p to state theta. Let CTP of theta denote the event that state theta is commonly p-believed after T signal draws. So this means that all players individually p-believe state theta. They p-believe that all other players p-believe state theta. They p-believe that all other players p-believe that all other players p-believe state theta, and so on along the entire infinite hierarchy of beliefs. So Cripps, Mailath, and Samuelson's result is that for each information structure, agents are going to commonly learn the true state, in the sense that for any p and for each state theta, the probability that players achieve common p-belief of the true state theta converges to 1 as the number of signal draws goes to infinity. So this is saying that as T goes to infinity, all information structures eliminate both first order and higher order uncertainty. But what we're going to be interested in is how to compare different information structures in terms of how effectively they eliminate first order and higher order uncertainty away from the limit. And so specifically to formalize this, we're going to be interested in what is the rate of convergence to common p-belief here under each information structure. So this is going to allow us to compare the probability with which different information structures induce common p-belief at all large but finite T. So this question about the rate of common learning or speed of common learning is going to be my focus for most of the talk. But then in the final part of the talk, I'll apply our answer to this question to characterize a ranking over information structures in terms of their value in coordination problems that are played after players observe a large but finite number of signal draws. Okay, so before going into the analysis, let me just illustrate this question about the speed of common learning by means of a simple 2x2x2 example. So here we have two agents, we have two states, a high state and a low state. And for each, and the information structure is a simple binary information structure where for each agent, her set of private signals is simply the set of states, and where the joint signal distribution in each state theta is parameterized by two parameters. First, there's an individual precision parameter gamma between 0.5 and 1. So this captures the probability with which each agent's signal matches the state. So the probability that x1 is equal to theta is going to be gamma in state theta, and likewise the probability that x2 is equal to theta is equal to gamma in state theta. And then second, there's a correlation parameter rho, which captures how correlated agent signals are. So the higher rho, the more correlated our signals. In particular, if rho is equal to 1, that would mean that signals are perfectly correlated. Okay, so in the context of this simple example, our question about the speed of common learning then boils down to asking if you have two parameter combinations, gamma rho and gamma tilde rho tilde, under which of these two is common learning going to be faster? And so here, intuitively, a higher gamma should be helpful because this is going to reduce first order uncertainty if both players' individual signal precisions are higher. But one might think that rho should also matter because rho affects players' higher order uncertainty about other players' signals. And hence, one might think that this should also matter for the probability of common learning. And so ex ante, it might then not be obvious how to compare these two parameter combinations, how to trade off these two considerations between individual precision and correlation. But our general results are going to allow us to answer this question. And so let me then present our general characterization of the speed of common learning, returning to the general setup. For this, let me first recall a standard statistical measure of the speed at which a single agent individually learns the state. So for this, we consider a single agent I and suppose the true state is theta. Then we can measure how easy agent I finds it to distinguish any other state, theta prime, from the true state theta, by considering the Chernoff statistical distance. So I denote this by d of mu I theta prime. And what this considers is the minimum over all signal distributions mu I of the maximum between the Kullback-Leibler divergence of mu I relative to mu I theta and mu I relative to mu I theta prime. Now, if you look at this for a moment, it will become clear that at any minimizer nu I here, it has to be that these two KL divergences are equalized. So what this Chernoff distance is simply capturing is the distance from I's signal distribution in state theta and I's signal distribution in state theta prime to their midpoint in terms of KL divergence. So the smaller this distance, the closer are these two signal distributions to each other. And hence, the more difficult it is to statistically distinguish the two states based on observing repeated signal draws from either of these distributions. Okay, so using the Chernoff distance, we then, oh, was there a question? Yeah.
Mira, I'm sorry for interrupting. Would you mind telling me this, what this KL midpoint is? I'm sorry, I don't know. That's probably something very basic.
Yeah, so the Kullback-Leibler divergence, right? That's a measure of distance between statistical distributions, between probability measures. And so what I mean by KL midpoint here is simply that the minimizer mu I in this expression is equally close to mu I theta and to mu I theta prime in terms of KL distance. So, so if you have two distributions, mu I theta and mu I theta prime, we're going to look at the distributions mu I that are equidistant from the two. And so those can be viewed as the midpoint. And this Chernoff distance simply captures the distance to this midpoint. Does that answer your question?
Well, I'm afraid I don't know what this KL means.
So the Kullback-Leibler divergence is, I should have written it out. So this is looking at the expected log likelihood ratio of signals under mu I and mu I theta, where the expectation is taken relative to mu I here. So intuitively, this is capturing how far apart the observed signal distribution mu I is relative to some reference distribution mu I theta.
Okay, thank you.
Yeah. Okay, and so using this Chernoff distance, one can then characterize agent I's speed of individual learning in state theta as follows. So the speed is exponential in the sense that the probability that agent I achieves individual p-belief of the true state theta converges to 1 at this exponential rate, lambda I theta, where lambda I theta simply considers the lowest Chernoff distance between mu I theta and mu I theta prime in any other state theta prime. So to characterize the speed of individual learning, one focuses on the state theta prime that is hardest for agent I to distinguish from the true state theta. And so this then gives us a measure of an individual agent I's learning efficiency. So our first main result is that to characterize the speed of common learning, we can simply consider the following simple multi-agent learning efficiency index. So this I'm going to denote by lambda theta. And what this does is to simply take the minimal individual learning efficiency index across all agents I. So this multi-agent learning efficiency index simply considers the slowest agent's rate of individual learning. By contrast, it does not depend at all on the correlation across different agent signals. So for instance, in the previous binary example, where the information structure was parameterized by an individual precision parameter gamma and a correlation parameter rho, this learning efficiency index is going to be strictly increasing in individual precision gamma, as we expected, but it's in fact completely independent of the correlation parameter rho. And so our first main result says the following: fix any information structure I, then for each state theta and each p, the probability at which players achieve common p-belief of the true state theta converges to 1 at exponential rate given precisely by this multi-agent learning efficiency index. And moreover, the same is true of the probability of individual p-belief. So the probability that players achieve individual p-belief of the true state also converges to 1 at the same exponential rate. Okay, so let me discuss this result a little bit. So the second part, that the probability of individual p-belief converges to 1 at rate given by our multi-agent learning efficiency index, that's just immediate from the preceding characterization of the speed of single agent learning. The substantive part of the result is the first part about the speed of common learning. And so here, note that common p-belief is, of course, a much more demanding notion than individual p-belief. It requires confidence, not just in terms of players' first order beliefs about the state, but it requires their entire infinite hierarchy of beliefs to become confident. And so based on this, it might then be natural to expect, and indeed that's what we expected when we started working on this paper, that common learning should be slower than individual learning. However, what this result is showing is that as the number of signal observations grows large, common learning and individual learning, in fact, occur at the same rate which is given by this multi-agent learning efficiency index. And so as I'll illustrate in a moment, the key idea behind this result is that under every information structure, higher order uncertainty vanishes faster than first order uncertainty. And so for this reason, when it comes to looking at the speed of common learning, this simply ends up boiling down to the speed of individual learning. This is further reflected by the fact that this learning efficiency index, lambda theta, does not depend on the correlation across different players' signals. So if players observe just few signal draws, then it's easy to see that the probability of common p-belief will in general be affected by the correlation across their signals. However, what this result shows is that under sufficiently large samples of signals, correlation across agent signals has a negligible effect on common p-belief, and all that matters is kind of individual signal, players' individual signal informativeness. Okay, so let me briefly illustrate the idea. Yeah, are there any questions? Yeah.
Yeah, so the theorem applies to the example, or it's a more general?
This is more general. So this applies to our general setup, which so the only key substantive restriction is really that states and signals are finite, and I can say a little bit more about that towards the end.
And what is raw then in the general case? It's the
Oh, there's no single parameter row necessarily, but we have the joint distribution. So if we go back to the general setup, we have a joint signal distribution in each state theta, right? And this can be arbitrary, so this can display arbitrary correlation across different players' signals.
So I understand. So rho is undefined in the general for general information structures?
Yeah, there's not necessarily a single correlation parameter row for general information structures, but this joint signal distribution could display arbitrary correlation. But note that the learning efficiency index depends only on the marginal signal distributions, because each of these individual learning rates depends only on player I's marginal signal distribution in each state. And the multi-agent learning efficiency index is looking just at the lowest individual learning efficiency index. So this tells you that correlation doesn't matter. All that matters is the marginal signal distributions of different players.
I see. Okay.
Yeah.
So sorry, Mira. So
yeah.
So somehow you say that because of the correlation doesn't matter too much, then somehow it causes that the higher order uncertainties are vanishing faster or not as important as first order ones. So those things are somehow related?
Yes, those two things are kind of in a way two sides of the same coin. So it's really these two findings are related, and I'm now going to illustrate why that's the case. So
if you would use another information stuff to measure the learning speed or something, then you would get something else. Because in this case, the correlation doesn't matter. So because of the correlation doesn't matter, you get the higher order uncertainties. Not too important.
So this is a result. So the result is that correlation doesn't matter. So our index doesn't feature correlation, but this turns out to be the right index to capture the speed of common learning. So the result is really that common learning, the speed of common learning only depends on marginal signal informativeness. It does not depend on the correlation across different players.
See. So if this index depends on the marginals only, then the correlation doesn't matter, and then because of this, the higher. Okay, thank you very much.
Yeah.
Okay, I see.
Yeah. Okay, so let me maybe illustrate the kind of basic idea behind this main result by again revisiting our illustrative example. So I'm going to assume specifically that the individual precision parameter is 3/5 here and correlation parameter is 5/12. So this gives rise to the following joint signal probabilities. And so note that with these specific parameters, the two player signals are in fact going to be negatively correlated, but this is not important for our general arguments. Okay, so
I still have a little question.
Yeah.
the theorems are formulated for a fixed P, right?
For any P, so for fixed, but any P,
Yeah, but for fixed P, so the probability, but then it seems that it doesn't reflect really high order uncertainty or anything. I mean, there should be something that allows P to go to 1.
Yeah.
So you can approach common knowledge really.
Yeah. So yeah. But P can be arbitrarily close to 1 here, and note that the index does not depend on P. So the rate of convergence is the same no matter how close P is to 1. So even for P very, very close to 1, the rate of convergence to common P belief will still be the same as the rate of convergence to individual P belief.
Yes, still I would say, okay, but still P can be very close to 1, but fixed, and then, okay, and then the rate of convergence is dependent of P. But the question is whether in some sense, when you accumulate more and more signals, you converge to C1 of P theta with probability 1.
Yeah, I see. So you want P to actually be 1. Yeah, so we can get arbitrary.
P will not be 1, but I want really P to converge to 1.
Yeah, we can let P converge to 1. I guess it's sort of an order of limits question you're asking. So we're saying fix P and then let T grow large, and then the rate of convergence is going to be given by this index. Maybe you want a different rate of convergence. And so note that there is this little O of T term here, which becomes negligible as T grows large, but this little O of T term could in principle depend on P, and indeed will depend on P. So maybe that's something you would be interested in.
If I try to let both T and T to infinity and P to 1, then the rate may change.
Yeah, so I think the rate might still be this rate, but I guess the point at which, so this result is going to sort of kick in when T is sufficiently large. So when T is sufficiently large, the rate here will dominate the little O of T term, but just how large T needs to be for that depends on what the little O of T term is, and so that might depend on P.
I see. Okay.
Yeah. Okay. Okay, so I'm going to revisit this illustrative example with these particular parameters, and under these parameters, signals are negatively correlated, but this is not going to be important for the general arguments. And so let mu IT denote I's empirical signal distribution up to T. So this keeps track of the fraction of each signal that player I sees after T signal draws. And note that this is a sufficient statistic for I's first order and higher order beliefs. And so I'm going to suppose that the true state is the high state and that T is sufficiently large. Then note that at large T, the event that players have individual P belief of the high state can be approximated by the event that each player's empirical signal distribution has fraction greater than a half of the high signal. So this is depicted graphically here by this square, where I'm viewing this as a subset of the space of the product space of 1's empirical frequency of the high signal and 2's empirical frequency of the high signal. And so this approximation is intuitive. So, if T is sufficiently large, then I is going to become confident in the high signal, in the high state, if the majority of I's signals matches the high state.
Just a moment. Why is it true at large T? What's the importance of half? I'm missing something here, most probably.
Oh, so this is the 2 signal 2 state case, right? And the high signal is more likely in the high state because gamma is greater than a half, and the low signal is more likely than the low state. And so in the long run, players' first order beliefs are going to concentrate on the state for which you've seen more signals. And so if you've seen more high signals, in particular, more than half of your signals are high signals, then at large T, you're going to concentrate on the high state in your beliefs.
And it's independent of P again, right?
Yeah, this is independent of P. And by contrast, the event that players have common P belief of the high state is a strictly smaller event. In particular, in this setting, This can be approximated at large T by the event that both players have seen fraction greater than a half of high signals, but also greater than less than 9/11 of high signals. So this corresponds to the smaller square within BTP. So what's the idea here? Where does the 9/11 come from? So with these parameters I've chosen, one can see that if agent I observes fraction greater than 9/11 of high signals, then because the two player signals are negatively correlated, I is going to expect that player J, in fact, saw a fraction less than a half of high signals. So I is going to expect that J becomes confident in the low state, in the wrong state. Whereas conversely, if I does observe a fraction of high signals that is between a half and 9/11, then I is going to expect the same to be true for player J. So she's going to expect that J also saw between a half and 9/11 of high signals. And so based on this, one can then show this approximation of the set of the event that common P belief obtains. Okay, so what this means then is that we can decompose the event that common P belief fails into two different types of failures. So first we have what we call first order belief failures. So this is where at least one player fails to have individual P belief of the high state. And so this is depicted here by this gray region, which is just the complement of BTP. So this is where at least one player observed fraction less than a half of high signals. And second, we have higher order belief failures, which is the case where both players do have individual P belief of the high state, but they don't have common P belief. And so by the preceding approximations, this is given by this blue region here, where both players have seen fraction greater than a half of high signals, but at least one player has seen fraction less than 9/11, has also seen fraction greater than 9/11 of high signals. And so to understand the speed of common learning, what we then want to understand is the rate at which both these types of the probability of observing both these types of failures vanishes as T grows large. And so here, the key insight of our argument is going to be that at large T, the probability of higher order belief failures, in fact, becomes negligible relative to the probability of first order belief failures. And so all that matters for the speed of common learning is going to be how fast these first order belief failures vanish, which will be given by our learning efficiency index. And so formally, to show this, note that both the higher order belief failures and the first order belief failures become very unlikely events as the number of signal draws grows large. So to analyze how fast these very unlikely events decay, we're going to have to use large deviation theory. So specifically, we use Sanoff's theorem from large deviation theory, which says that for any set D of joint empirical distributions, the probability that players observe an empirical distribution in D conditional on the high state decays exponentially at a rate given by the Kullback-Leibler divergence between D and the theoretical signal distribution in the high state. So the further this event D is from the true theoretical signal distribution in the high state, the faster its probability decays as the number of signal draws grows large. And so applied then to the current simple example, this result tells us that to find the rate at which the probability of first order belief failures decays, we can look at the KL distance from either player's theoretical signal distribution in the high state to this region here in gray where we have first order belief failures. So the rate at which the probability of first order belief failures decays can be represented by the KL distance corresponding to either of these solid arrows here. In contrast, the rate at which higher order belief failures decay for this, we need to look at the distance from the theoretical distributions to this blue region where we have higher order belief failures. And so this rate can be represented by either of these dashed distances here. And so note now that the dashed distances are greater than the solid distances. And so this then tells us that the probability of higher order belief failures decays faster than the probability of first order belief failures. Indeed, because these are exponential rates, this tells us that the probability of higher order belief failures becomes negligible relative to the probability of first order belief failures at sufficiently large t. And so the rate of common learning then just boils down to the rate of individual learning, which is given by the learning efficiency index. Okay, so beyond these graphical illustrations, what's the general idea here? So why is it that the probability of higher order belief failures vanishes faster than first order belief failures? So to establish this, we prove the following key information theoretic lemma. So for this, we're going to assume that player I observed some particular empirical distribution nu it. And then conditional on I observing this nu it and on state theta, we're going to consider I's expectation of J's observations, of J's empirical distribution, nu jt. Okay, so we're considering I's expectation of J's empirical frequency nu jt conditional on her own observation nu it and on the state being theta. And so this key lemma says the following. For all t and all empirical signal distributions, nu it observed by agent I, the distance between I's expectation of what J has observed and J's theoretical distribution in state theta is smaller than the distance between I's own signal observations and I's theoretical distribution in state theta, where these distances are again in terms of KL divergence. And moreover, this inequality is strict whenever nu it doesn't happen to exactly coincide with the theoretical distribution and when the joint distribution nu theta has full support. Okay, so in words, what is this lemma saying? So this lemma is saying that if I forms an expectation or an estimate of J's signal observations based on her own signal observations, then that estimate is going to be less atypical relative to the theoretical distribution than I's own observations. So I expect J to see signals that are less atypical than her own. For example, if signals are independent across the two agents, then I's own signals don't convey any information about J's signals. So I is always going to expect J's empirical distribution to just be the theoretical distribution in state theta. So this left-hand side will be 0. On the other hand, if signals are perfectly correlated, then I expect J to see exactly the same signals as herself. And so this inequality is going to hold with equality. And so this lemma also captures all other cases in between, the case of negative correlation. And so this inequality holds in all those cases. And so in the proof, we then use this lemma to show more generally that the probability of higher order belief failures vanishes faster than that of first order belief failures. And so let me just briefly note that the proof of this lemma uses the chain rule for KL divergence. So this is one of the central results in information theory. And so incorporating these information theoretic arguments is one of the key ways in which we refine the analysis in Cripps, Mailath, and Samuelson to obtain a characterization of the rate of common learning, as opposed to just showing that common learning occurs.
So Mira, sorry. So
yeah.
Looking at this lemma, so
yeah.
suppose I'm player I or agent I, and somehow at point T, my mu is exactly my mu.
Yeah.
So somehow I'm very, very precise. So on the right-hand side, I have 0, if I understand correctly.
Exactly. So then the right-hand side would be 0. And so in that case, the inequality is just an equality.
But why should I think that you also know precisely your distribution? Because I know that my distribution is the real one. So what is the intuition? So why I think that you are at least as well informed as I am, right? That's the dilemma.
Yeah. So you always, in some sense, you always think that your in expectation, at least your signals can't be any more atypical than my own. Exactly. Yeah. So I see. So yeah. So one, I'm not sure if it's a particularly good intuition, but one way of thinking about this is, so another way of interpreting this result is in terms of what's known as the second law of thermodynamics for Markov chains. So you can think of and this relates, of course, to work by Dobb. You can think of this process of expectations over other agents' signal observations, given my own signal observations, as defining a Markov chain over the space of signal observations. And so what this lemma is in some sense saying is that if you iterate this Markov chain, then as you iterate it, you become closer and closer to the stationary distribution or to the initial distribution. My own observation is kind of the first step. And if I now take the expectation, I'm iterating the Markov chain one step further, and that brings me closer to the initial distribution. So that's kind of capturing the mathematical intuition for why this result holds, and so this result is then translating this into the sort of statements about own signal observations versus other signal observations, which then translate into higher order belief failures versus first order belief failures.
Let me say something, but T is fixed, right, in the lemma?
Yeah, so this holds for all T.
Yeah.
And the reason we need T to then be large for our theorem is because this is just a result about expectations of opponent signal observations. But we then combine this with kind of law of large numbers arguments to show that when T is sufficiently large, I am very confident that opponents' signals will in fact concentrate on this expectation. Yeah, so this lemma holds for all T.
Yeah, but then the case that Miklos mentioned, on the right-hand side, you'll have 0, and so also the left-hand side is 0, right?
Exactly, yeah.
So the explanation in terms of a Markov chain, the Markov chain, what change in the Markov chain is T, right?
So the Markov chain is these expectations. Yeah, maybe this was confusing to say without additional notation, but the idea here is, so the first step is my own empirical frequency. Then I take the expectation over your empirical frequency. So I go from I to J, and then this Markov chain would continue by now looking at J's expectation of I's observation, but all this for fixed T. So you can completely ignore T for this Markov chain. Okay, great. So any other questions about this result?
Just me again,
yeah.
Sorry. So end of the day, so everything, all results depends on your index where you use at the beginning.
Yeah.
Okay.
Yeah.
And you said it's some minutes ago, you told me that it turned out that index is the good one.
The right index. Yeah.
The right. Yeah. Okay. You use the right word right. For me, this lemma is very surprising somehow. So it says me that I would say that in learning, I can imagine that I think that somebody missing the point much more than I miss.
Yeah. Yeah.
But it doesn't allow it.
Yeah, so it turns out that that's not the case. So I always expect opponent signal observations to be less atypical than my own.
So then why do you use that index? Why do you say that the index at the very beginning is the right one?
Is the right one? Yeah, so again, so this is really we didn't choose to use this index. This is just a result. So I could have written this result as saying the speed of common learning is characterized by this index, which happens to be given by the index here. So the result is that the speed of common learning occurs at this particular rate. And that's why I'm saying this is the right index. This is the index that captures the rate.
In this sense. Okay.
Exactly.
Okay, thanks. I see. Thank you.
Yeah. Okay, so I guess I have kind of 10 minutes left to go. Is that right?
Yes.
Okay.
Yes.
Okay, perfect. So then let me use the final part of the talk to then briefly explain how we use this first result about the speed of common learning to obtain a ranking over information structures in terms of their value for coordination problems. And so for this, we augment our basic learning environment as follows. So a basic game, G, consists of a finite action space, AI for each player I, and a utility UI over action profiles and states for each player. And so we're going to be interested in the setting where such a basic game is played after players have observed T draws of signals from some information structure. So in other words, we're considering an incomplete, static incomplete information game where information is parameterized by the number of signal draws T from I. So we're going to denote this game by GTI. And we're interested in the Bayes-Nash equilibria of GTI. And so to compare these equilibrium outcomes under different information structures, we're going to associate with each game G an objective function W over action profiles and states. So you can think of this as capturing, for instance, utilitarian welfare in the game, but it could also capture designers' preferences that don't necessarily have to relate to players' utilities in any particular way. And we assume that in each state theta, there's a unique optimal W optimal action profile, A theta W of the game. And so then to evaluate equilibrium outcomes under different information structures, for each information structure I and T, we're going to consider the ex-ante expectation of this objective W under the best Bayes-Nash equilibrium of the game. So I'm going to denote this by WTGI. And so our goal is, given any two information structures I and I tilde, we want to characterize when this objective that we can obtain under information structure I exceeds that under information structure I tilde for all large enough T, and ideally for a rich class of games G and objective functions W. And so in particular, it turns out that our learning efficiency index will allow us to rank information structures in a way that they that the ranking applies robustly across the following class of games and objective functions. So we impose one key assumption, which is a joint assumption on the game and the objective function, and we call this alignment at certainty. So this says that for each state theta, the W best action profile, A theta W of G, is a strict Nash equilibrium of G under common knowledge of theta. So this is saying that under common knowledge of the state, the first best objective is strictly achievable in equilibrium. And a leading example where this is satisfied is the motivating example where W would be utilitarian welfare and G would be a coordination game, where the efficient coordination is an equilibrium under common knowledge of the state, but where first order or higher order uncertainty impede efficient coordination. I'll illustrate this in a moment in the context of a coordinated attack game. Note that this assumption is much weaker than assuming that we're in a common interest game where all players' utilities are the same. So in a common interest game, we would have full alignment where players' incentives and the objective are fully aligned even away from common knowledge. Here, we're just saying that these are aligned at the common knowledge limit. Okay, and then for today's talk, I'm also going to impose the following assumption for expositional simplicity. This can be dropped. It just makes the statements a little bit more complicated. And so the second assumption says that for each player I and any two distinct states, player I's action in the efficient action profile in state theta is different from her action in the efficient action profile in state theta prime. So in other words, this is saying that the first best outcome requires all players to distinguish all states. Okay, so let me just briefly illustrate this assumption in the context of a coordinated attack game. So we have n players. Each player has 2 actions, attack 1 or not attack 0. There are 2 states, a high state, which is the state that's favorable to attack, and a low state, which is the state that's unfavorable to attack. And each player's utility UI is such that if she attacks, she incurs a cost of C, and she obtains a payoff of 1 if and only if the attack is successful, which happens if and only if the state is high and at least k players attack. And otherwise, she obtains a payoff of 0. So in this game, the utilitarian efficient actions are for all players to attack in the high state, no players to attack in the low state. And note that these are indeed strict Nash equilibria under common knowledge of the state. And so this means our alignment at certainty condition is satisfied, and the second assumption is also satisfied. Okay, so our second result then is that we can use our learning efficiency index to rank information structures in terms of their value for all these environments. So specifically, we consider an ex-ante version of the learning efficiency index. So denote this by lambda of I, which considers the worst case learning efficiency index across all states theta. Then our second result says the following. Take any 2 information structures I and I tilde such that I has a higher learning efficiency index. Then for any game G and objective W satisfying the 2 assumptions, there exists a large enough number of signal draws T such that whenever players observe more than T signal draws, then the expected objective under I will exceed that under I tilde. So this result provides a generically complete ranking over information structures that applies in any coordination problem or other game and objective satisfying our assumptions, as long as we're in a sufficiently data-rich environment where players have access to sufficiently many draws of signals. The ranking is generically complete because it can rank any 2 information structures whose efficiency indices are different. If the indices are exactly tied, the ranking is silent. And so this applies robustly across all these environments. And so the fact that this applies robustly across all these different environments, G and W, relies crucially on our first finding that the speed of common learning is equal to the speed of individual learning. And so let me now illustrate why that's the case. So to illustrate this, let's go back to the coordinated attack example. And so there, to show that lambda I provides the appropriate ranking over information structures, it suffices to show that lambda I is the fastest rate at which any BNE sequence can converge to the efficient outcome in each state. And so why is that? Why is this the case? So for this, we need to show 2 things. First, we need to show that we can reach efficiency at least at this rate, lambda I. But this is pretty clear from the first result, because note that common P belief for P sufficiently large is going to be sufficient for players to achieve efficient coordination. This is because we're assuming that the efficient outcome is a strict Nash equilibrium under common knowledge, which then means that as long as P is sufficiently large, this can be played as part of a BNE sequence whenever players have a common P belief of the state. And so we saw by the first result that lambda I is the rate at which players achieve common P belief of the state, so their rate of common learning. And so this then means this provides a lower bound on the rate at which players can achieve efficient coordination. What's perhaps less clear is why can't players converge to efficient coordination any faster than this rate? Because note that if the number of players k that are required for a successful attack is less than the total number of players, then common p-belief is not necessary for all agents to be willing to attack. However, note that at the very least, we need individual p-belief for some p for agents to be willing to attack. And so for this reason, it then again turns out that inefficiency can vanish no faster than this rate lambda I, because we saw that this is not only the rate of common learning, but also the rate at which players individually learn the state. So that's the basic idea behind Theorem 2. And so let me just briefly highlight some implications this result then has for designing information in coordination games. So what this result suggests is that in data-rich settings where players have access to many signal draws, a designer who's seeking to facilitate efficient coordination should follow kind of two general principles. First, the designer should focus only on improving individuals' first order information about the state, so their individual informativeness of signals. In contrast, kind of providing additional signals about other players' signals that don't convey direct information about the state has a negligible effect in these data-rich environments. And so this contrasts perhaps with the kind of conventional wisdom in the higher order beliefs literature that uncertainty about other players' signals can be a significant source of inefficiency in coordination games. But the reason this holds in our setting is precisely because of this key insight that we've seen that higher order uncertainty becomes negligible relative to first order uncertainty as the number of signal draws grows large. And so in data-rich settings, what the designer should focus on is simply making first order information as precise as possible. And then second, the designer should also be egalitarian in the sense that she should should focus on improving the worst informed agent's information about the state. And that's because, as is captured by this learning efficiency index, the speed of common learning is the same as the slowest player's speed of individual learning. So all that matters is how fast the worst informed player learns the state. Okay, so let me conclude then. So in this paper, we've conducted a comparison of multi-agent information structures in a learning setting. Our key result was to characterize the speed of common learning under each information structure. And we then use this to show that information structures that lead to faster common learning induce more efficient equilibrium outcomes in any coordination game that is played after sufficiently many signal draws. Kind of the key insight that I've iterated many times on which this paper relies is to show that higher order uncertainty vanishes faster than first order uncertainty, as was formalized by this key lemma I showed. And so we use this to show that the speed of common learning simply boils down to the slowest player's speed of individual learning. And this also had the implication that the multi-agent learning efficiency index that characterizes the speed of common learning does not depend on the correlation across agent signals. And finally, I highlighted some implications for information design in games with rich data. Okay, I think I'm actually slightly over time, so my apologies. Thank you very much for your attention.
Thank you.
I have a little question. Can you please go back 2 slides?
Mm-hmm. Yeah. Cool.
No,
Sorry,
no.
so going ahead. Yeah. Here.
Okay. No. Next.
Next.
Yes. Okay.
Yeah.
What you showed is that when you compare, you fix a model, you fix an information structure.
Yeah.
Then it turns out that common learning happens in the same rate as individual learning, right?
Yeah.
How can you conclude from this that adding signals about other signals has negligible effect? Because now we are comparing 2 different models.
No, so these would be two different information structures. So you could compare information structures where we leave the marginal signal distributions unaffected, and all we're doing is changing the correlation. So that's what I'm trying to say with this. So each player's marginal distributions of private signals in each state are the same, but I make them more correlated, which can be understood as saying I provide more information to players about the signals that other players have seen.
I see. What if you add signals about the signals that others are seeing? Is it the same as you?
Yeah, so I guess it depends on how you formalize it. So they have to be added in such a way that these signals don't change the marginal distribution. So my signals about your signals shouldn't convey information about the state. If they do that, then that will improve my marginal informativeness, which is helpful.
Yes.
Exactly. But if say my signals and your signals are both kind of the state plus some shock, and all I do is, as a designer, I give you some information about what the other agent's shock was, that would kind of fit the setting I have in mind here.
Okay, good.
Yeah.
Okay, any other questions?
And there are questions in the chat, Mira. Can you read them, or I should read out?
I see. Okay, so the question is I think Cleota already responded, but so to what extent do your results depend on your choice of KL divergence as the measure for statistical distance? Have you considered using a distance metric? So again, this is not really an assumption of us that we've decided kind of arbitrarily to use KL divergence. This is what is needed to characterize the exponential rate of learning. So in the individual learning setting, we already saw that the rate of individual learning is given by this Chernoff distance, which is based on Kullback-Leibler divergence of states. So that's just the characterization of the speed of individual learning. And if one used some other distance-based metric, this characterization would not hold. It's important that this is the Kullback-Leibler divergence. And likewise for our multi-agent index, the result says that the rate of common learning is given by this index. So this is the correct notion that is needed to capture the rate of common learning. And kind of mathematically, the reason this is needed is to apply large deviation theory arguments. So Sarnoff's theorem that I mentioned relies crucially on using Kullback-Leibler divergence as the notion of statistical distance.
So do you regard this as extending Chernoff in some sense?
Yeah, I think you could view it as extending Chernoff to settings with multiple players, and so higher order uncertainty instead of just first order uncertainty. And then in that sense, in a nutshell, the insight is that even though you might expect that higher order uncertainty should add something beyond Chernoff, in a sense it doesn't. It just boils down to the slowest player's Chernoff informativeness. Yeah.
Mira?
Yeah.
Would you mind going back to the slide where you have the definition of CTP of a common knowledge?
Yes. Yeah, I should have, of course, credited Doug for this.
Thanks. Okay, so the event BTP, so that's a subset of this sequence of the sequences of signals, right?
Exactly. Yeah.
Okay. And you're looking at the probability for CTP to go to 1 conditional on theta.
Yeah.
So I was wondering about a slightly different event. The event that at some finite time, we achieve common P knowledge, or P common knowledge, and we stay there for the rest of time.
I see. So you mean you want there to be no possible reversal or something?
Exactly. How? So is this result still true? The equation 1, would that still be true? That with probability 1, we obtain this kind of learning?
Yeah, I think that's true, because you do. I mean, you converge to 1, so you get arbitrarily close to 1, and then you also stay there. So at some t, you're going to be within epsilon of 1, and then if t is large enough, it will stop oscillating, and you will reach 1. So I think that's the case. I think for our result about the rate, it would be slightly trickier. So what our result is giving us is kind of a large enough t after which the probability of common p-belief under one information structure is always higher than under another, but it's not saying that this probability, both of these probabilities are monotonic in t necessarily. It's just that one is higher than the other at all t greater than this cutoff t. Did that make sense?
It makes sense, yeah. But I was wondering about a slightly different. Instead of looking at the so maybe this is true trivially. I just can't see it right away. But it seems an interesting sort of question as well. It's a different, possibly a different question. So instead of looking at the limit of the probability at any given t, so we'll look at one single event. That there is a finite time. After which we are in the event CTP. So that
with probability 1 in finite time. I see.
That CTP obtains for any t after t star. Basically, that's
with probability 1. I see. Yeah, with probability 1, I don't think that's going to happen in most non-trivial information structures.
Yeah, that's interesting. Thank you.
Any more questions? Apparently not. Okay, so we will thank our speaker today for a very interesting presentation. And we hope to see you at the next One World seminar meeting in 2 weeks' time.
Yeah, thank you again for the attention and for all the great questions. Thank you.
Hello.
Bye, everybody.